In this video, we're going to talk about compound interest. So I actually want to begin with an example right away. So suppose that you invest $1,000 and earn 8% interest per year. Part A is asking how much do you have after 1 year and then after 5 years. So let's think about 1 year. So for 1 year, let's think about how much interest we'd have first. So what is our 1 year interest? So to determine how much we end up getting in interest, you have to take your investment amount, so the 1,000, that initial amount, and multiply it by the interest rate converted to a decimal. So 8% as a decimal is 0.08, and we could multiply this out and get a number, but I want to just keep it as it is for the time being to illustrate what the formula is going to be in general. So now that we know the interest for 1 year, what would the 1 year total be? What would the total amount of money that we have after 1 year be? Well, we do also have the initial 1,000. And let's add to that how much money we make in interest. So let's add to that the 1,000 plus 0.08, times 0.08. And we can factor a 1,000 out of both of these terms and get 1,000 factored out times 1 plus 0.08. Because when you factor a 1,000 out of the first term, there will be 1 left over. So we can simplify. We get 1,000, and then 1 added to 0.08 is 1.08. So we end up with the initial amount times 1.08. And if you multiply that, we will get $1,080. Okay, so that's how much we have after 1 year. What about after 5 years? So if we talk about our 5-year total. Well, so if we keep getting interest, 8% every single year on that initial $1,000 investment, what we'd end up doing is we'd end up doing the 1,000, and after 1 year, we ended up multiplying it by 1.08. After 5 years, we'd multiply by 1.08 5 times. So overall, we'd multiply by 1.08 to the 5th power. That's the same thing as multiplying by 1.08 5 times. Okay, and this, I went ahead and worked this out with a calculator, so I'll tell you what this is. This is approximately 1469.32808 if I round that to 5 decimal places. Okay, so now I want to state the formula in general. So if we have interest like this that is compounded just once a year, and I want to know how much we will end up having after t years. So after some amount of time. So I'm going to write down an equation for that amount. I'm going to call that amount a of t. Okay, and a of t will be equal to, I'll write down the formula, and then I'll explain what it means. It's going to be p times 1 plus r to the t power. So let me explain now what each part of this means. So p is like the 1,000 here. It's the initial amount. It's called p because this is often referred to as the principal. The principal investment, the initial investment. Okay, r is the interest rate. So that was the 0.08. When we add 0.08 to 1, that's where we got the 1.08 from. So it's the interest rate, but as a decimal. Interest rate as a decimal. T, I think, might be the easiest to identify. T is the number of years here. The number of years. And then finally, what is a of t? Well, a of t is, once we work out whatever the right-hand side is, it's a of t represents the amount after t years. So it's how much money we would have after t years. Okay, so let's do another part to this example, part B. How much should you have invested to have 20,000 after 10 years? Okay, so now it's saying that after 10 years, so t equals 10, we want to end up with 20,000. So 20,000 is not the initial investment, it's not p, it's what goes on the left for a of t. It's the amount that we want to end up with. So we'll write 20,000 on the left, and that's going to equal p times 1 plus, so r, the interest rate we knew already. The interest rate was 0.08, remember? 0.08, and to the 10th power, because it says we want to do this for 10 years. So, and we want to know how much we should have invested, so that means we want p. So we can isolate the p. P is going to be 20,000 and divide by this 1.08 to the 10th power. Okay, and if we plug this into a calculator, we end up with, units are dollars, $9,263. I'm going to go to 5 decimals, 86976. But it's interesting to see that if we invested this amount at an 8% interest rate, after 10 years, it would more than double. So let's do another part to this example. Now, for part C, suppose that you instead invest $1,000, so the same initial amount that we began with, at an 8% interest rate, compounded quarterly. So compounded quarterly means 4 times a year. So that term quarter sort of refers to 4 times. Once for each quarter of the year. Okay, so 4 times in a year, we're going to accrue interest. So each time we get interest here, we're not going to get 8% every single time. That would be really, really high. What compounded quarterly means is they're going to take this interest rate, they're going to divide it into 4 equal pieces, and give us that interest rate 4 times a year. So we would get that 8% interest rate divided into 4 pieces. So 8 divided by 4, that's 2%. We're going to get 2% each time. Okay, so after 1 year, we would end up with, so it's the initial amount that we invest, the 1,000, times 1 plus the interest rate that we're getting. So we're actually getting like a 0.08 divided by 4 each time. And after 1 year, we will have gotten interest 4 different times, because we're getting interest every quarter, which is 4 times in a year. Okay, so notice that this 8% over 4, that is what we plugged into here. And the reason why this exponent is 4, we already sort of mentioned it in words, but I'll write it down. This is because we get interest 4 times in a year, because we're getting it quarterly. And if we work out what this is, with the calculator, this ends up being about $1,082.43216. And if we compare that with what we had before, with just getting the whole 8%, but only at the end of the year, it's a little bit more than that. That was actually 1,080, so it's a little bit more than that. What would happen if we do this after 5 years? How much would we end up with? Well, so we start with the initial amount again, the 1,000. We'd multiply it by 1 plus the interest rate, and we're dividing that 0.08 into 4 equal pieces. But how many times would we accrue interest? Would we get interest over a 5-year span? Well, we get it 4 times a year. Multiply that by 5 for 5 years. So this exponent again is because we are getting interest 4 times 5, 4 times a year, multiplied by 5 years, which is 20. We're getting interest 20 times in 5 years. And if we work out what this is with a calculator, this is 1485.94740. So 1485.94740. So I'm going to compare that with how much we had after 5 years, just compounding once a year instead of 4 times a year, but broken up into smaller chunks. But before we do that, let me just state the general formula. If we're getting interest that's compounded m times in a year, after t years, the amount that we'd have, I'm going to call it A of t for the amount, it's going to be P, so that's the principal, the initial investment, multiplied by 1 plus, we're taking our interest rate and we're dividing it into m pieces, and we're going to end up multiplying by, so we get interest m times in a year, but we're doing it over t years, so we have to multiply by t, and that's our formula. It matches up with what we were getting here, Okay, so now let's just compare. After 5 years, what were the numbers that we got when we got interest just once a year, so that's annually, and when we did it quarterly? So annually, we ended up with about, I'm just going to do it to the nearest integer, we got about $1,469. Compounded quarterly, we can actually see that number up here. It was about 1,480, if I round up because I have 0.9, about $1,486. So we end up with more if we're compounding more often. The reason for that, just on a conceptual level, is if we start getting interest, even if it's broken up into pieces like this, like it's 2% each time, 4 times a year, we start getting interest earlier. So after we get a 2% interest the first time, after 1 quarter, that initial amount, 1,000, is already a little bit bigger than 1,000. So when we get the next 2% interest, we're getting that next 2% interest on that already larger amount. And then when we get the next 2% interest, we're getting that on an already larger amount. Whereas when we do just 8% all at once, all of that 8% is being applied to the $1,000. Okay, so that's just kind of like a intuitive kind of explanation in words. But the key takeaway that I want you to have from this is that the more often it compounds, the better. The more often it compounds, the better it is. The more that we have. It turns out there's kind of like an upper limit to how good this can get. So even if I were to do something like compounding 1,000 times in a year, which is really, really high, that probably realistically wouldn't happen. Like this amount that I end up with won't just get like exceedingly high. There's sort of like an upper threshold for how high it can get. And that's what we're going to kind of segue into a little bit. But I want to ask a question to lead into that, which is, well, can we compound every single instant? So maybe not even 1,000 times, maybe even more, like every single instant. Can we get compound? And the answer is yes, at least in a mathematical sense. Yes, mathematically, this is called continuously. It's called continuously compounded interest. Or sometimes I might just say continuously compound interest. Okay, so how does this work? So if we're getting interest every instant, that means m, the number of times we're getting interest, m, that number, is getting infinitely large. Okay, so the number of times we're getting interest, which is m in a year, needs to get really, really big. So I'm going to let it get infinitely large. So as that happens, let's think about what would or I'm just going to tell you an observation about what happens to this thing in the parentheses. So I'm going to zoom out a little bit so I can still refer to it. So it turns out that as m gets really, really large, let's first write down what happens to 1 plus 1 over m to the m power. All right, so let's actually take a look at this with a calculator. Let's just plug in something that's really, really big for m and see what type of thing this is getting close to. So I'm going to use Wolfram Alpha for this. So I have like 1 plus 1 over, I need a really big number. So let's just go like 999, 999, so 6 nines, and then to the same power, so 999, 999, and we're getting something like this, 2.718 something, something, something. Looks familiar. So I'm going to go back to the notes. So I'm going to write down more precisely what this is approaching. It's approaching 2.71828. I'll just go that far in terms of the decimal digits. Dot, dot, dot. So remember, even when I plugged in 999,999, that's not the biggest thing I could have plugged in. I could have plugged in bigger and bigger things. The bigger and bigger I plug in, I eventually get something really, really close to this out. But this number looks super familiar. This is E. This is actually what E is. This is where E comes from. It shows up in continuously compounded interest. People noticed that when they plugged in a bigger and bigger number in for the m, that this whole expression seemed to approach this weird number, 2.718 something, something, something. And they decided to call that something. They decided to call that E. And it turns out this weird decimal shows up in other places. It shows up in other places in calculus as well. It showed up in so many places that they decided to give it a special name. They called it E. Okay, so well, what about our expression? Ours is a little bit different because it has an r and it has this t in the exponent. It turns out what our thing approaches is something really close. It's E, but to the rt power. Okay, so with that said, now let's write down a formula for continuously compounded interest after t years. Let me zoom out a little bit so I can still see my old formula. So it would be a of t equals p, and then this thing in parentheses, the 1 plus r over m to the mt power, we now know that's approaching e to the rt. So we get p e to the rt. Or sometimes people just call this thing PERT. So this is the formula for continuously compounded interest. All right, so now let's do an example where we use this. Okay, so part D of this example. Let's say you invest $1,000 again at 8% interest rate, compounded continuously. How much do you have after 5 years? This has been the recurring question in this video. Okay, so well, we take the 1,000, that's the p value, and we're going to multiply by e to the r, so r is the interest rate as a decimal, 0.08, multiply by t, which is 5. Okay, and if we plug that into a calculator, we'll end up with, so it's in dollars, 1,491.82470. And that's actually more than what we had in either scenario before. Remember, quarterly was $14.86. Now we did a little better, $5 better. And this is kind of the best that we can do in some sense. This is the best type of compounding. With this type of compounding, we're getting interest every single instant. So we can't really do better than this in terms of compound interest. All right, so let's look at one more example. So the example is that you buy a stock which returns a 5% interest rate, compounded continuously. How long does it take the stock to quadruple? So it's talking about interest rate that's compounded continuously, which means I need to use my a of t equals p e to the rt. I could use the version of the formula that has the e in it because it's continuously compound interest. So at this point, I want you to pause the video for about 2 minutes and think about how you would begin this example. It's probably not going to be enough time to finish it, But think about how you would get started. 4, 3, 2, 1, pause the video. Pause the video for about 2 minutes and think about how you'd get this one started. Alright, so hopefully you did that. Hopefully you've paused the video for about 2 minutes to think about how you'd begin. So what we need to do is, we need the initial amount, which was p, to quadruple. That means we'll end up with 4 times as much as what we started with. So what we end up with is a of t. We plug in what we end up with into the left-hand side. We're going to set a of t equal to 4p. In fact, let me put this in a different color. We're going to set a of t equal to 4p. So if I do that, the left-hand side becomes 4p. The right-hand side is p e to the, rt. And let me go ahead and plug in what r is. I know r is 0.05, and then I have t. And now I have this equation to try to solve. I can divide both sides by p, because that's going to be some number. 4 e to the 0.05t. The one thing that I have to be careful with is when I divide both sides by p, I would want to make sure that p is not 0. But if p was 0, that would mean we're investing nothing, which isn't realistic. So we'd assume that p is a positive number. So it's fine to divide by it. Okay, so at this point, I need to do some review of logs. So brief review. Let's recall that if you have an exponential equation, something like a to the x equals b. So this is an exponential form. You can always put something that's an exponential form and rewrite it in log form. So if we could transform this and write it in terms of the inverse, and the inverse of an exponential is a log, and you would end up with log base a. So the base of the exponent becomes the base of the log. So that's important. And then you'll plug something into the log, and you'll get something out of the log. And when you rewrite something in terms of the inverse, the input and the output switch. So x is what's getting plugged into the exponential function, which means I'm going to get it out of the log function. And b is the output of the exponential, so I'm going to plug that in to the log function. Okay, so I'm going to put this in a little bubble and say that the bottom version is what's called log form. And the other thing that I want to point out is, okay, so if we do that for our problem now, if we rewrite this in log form, we end up with, so the base of my exponent is e, so we'll get log base e of something equals something, and 4 goes inside the log, because I switched the input and the output, and 0.05t goes on the other side. Well, log base e has a special name. Log base e of something. Let's put this in gray actually. Log base e of something of x is written in a special way. This is written as ln of x. That's what ln of x actually is. It's a type of log. It's actually log base e. Okay, so let me put a bubble around this. That's another bit of review from logs. So what we have now is if I isolate the t equals ln of 4 divided by 0.05, and the units here are years. So if you're doing an interest problem and it doesn't give you any units for what time is, you can assume, the convention is to assume that it's in years. Okay, so if I wasn't allowed to use a calculator, I could stop and I could leave my answer in this form. If I needed to round it, this ends up being 27.73 years if I round it to 2 decimal places. All right, so we've finished goal 2. We've introduced this idea of compound interest and talked about what continuously compound interest is.